In this video, we're going to talk about vectors and vertices, which will tie into your triangle rendering project and all projects going forward. This is generally considered the Hello World program of computer graphics. That being said, there's surprisingly a lot that goes into this project, unfortunately. This may be the hardest project in the entire course if you're unfamiliar with computer graphics. There will be more sophisticated projects after this, but this project requires the biggest information dump that will likely be completely alien to you, and a lot of concepts you need to string together that are hardly related. That being said, for this video on vectors, you don't need to understand all the concepts in this video to make the project work. So if you couldn't grasp everything today, that's okay. There will be other chances, and you can always come back after this video. The bright side is that we're getting it out of the way early into the semester. You could definitely find this project online, but this is probably the most foundational project in the entire course, so if you do this, I think you'll end up regretting it. So let's just dive in. There's 3 points to a triangle. How do we represent these points? Even though this project will look 2D, we are going to use 3D coordinates to represent the points. This means that each point will have an x, y, and a z component. You can just keep the z component set to 0 for this project. You can imagine the x component going to the right, the y component going upwards, and you can think of the z component as coming out of the screen directly towards your face. Now, why does the z direction go towards you and not the other way? It's because the graphics world standardized on a right-handed coordinate system, except for Microsoft with DirectX, but that's just because Microsoft never knows what they're doing. The right-hand rule means that if you take your right hand and you point your thumb along the x direction and your index finger along the y direction, forming kind of an L shape, then your middle finger being perpendicular to both of those, it naturally points in the z direction towards you. We'll use this hand rule to keep ourselves oriented manually quite a bit in this course. Now, how are we going to represent these triangle points? We're going to represent them as 3D vertices. Vertices look like this in code. I'm going to be using the words points and vertices interchangeably, but vertices represent the points that make up a shape. So in this coordinate frame, this vertex, 1, 0, 0, corresponds to this dot, which has traveled in the x direction from the origin. This point, 0, 1, 0, has traveled in the y direction from the origin by the same amount. And this point, 0, 0, 1, has traveled in the z direction from the origin. I'm using kind of funny wording here when I say that a point has traveled in some direction from the origin, but that's because I'm trying to build up an intuition here for what are called basis vectors, which I'll get back into in a second. First, what is a vector? It's easiest to define vectors in terms of how they're different from vertices. Vertices, or points, are just exactly what you think they are, points in space, like these dots. Vectors don't have a location the same way a point or a vertex does. The only components of a vector are its direction and its magnitude. The tricky thing with representing vectors like this is that I have to give them a location so you can see them, but the location is completely arbitrary. Real quick, I should mention that as computer science students, you've probably seen vectors referring to array lists in things like C++. This is because C++ was created by someone working for AT&T, so he translated what it feels like to interact with AT&T into a programming language. This is largely considered a huge mistake in C++ history, and you should discard this way of thinking about vectors if that's what you're accustomed to. I tend to think of vectors manually as an arrow, like what you're saying. One slightly jarring thing is that in code, we typically represent vectors the same way we do vertices, which is confusing. So vertices, they'll have the data type of vectors. The way we tell them apart is usually just by giving the variables a good name. The reason vectors are represented this way is because we define them by where the tip of the arrow lands if we imagine that the tail starts at the origin. So in a way, we do sort of define vectors with points. The other obvious reason is that vectors contain 3 components, just like vertices, if we're talking about 3D vectors and vertices. So it's most convenient to just represent them with the same data type. Plus, this way, we don't have to worry about operations between different data types. Again, we're imagining that the tail starts at the origin, since vectors have no actual location. So let's take an extremely simple vector that points to the right. We'll represent it as 1, 0, 0. You can see that when we imagine the tail of this vector is on the origin, the tip lands on the point 1, 0, 0. So this vector is going in the x direction. I mentioned that the vectors have a magnitude. That's the same thing as saying that a vector has a length. In this case, the vector's length is 1. If the vector was instead 0, 0, 2, then the magnitude would be 2 instead. The 0, 0, 1 vector we first talked about is a unit vector because its length is 1. These special unit vectors that point perfectly along our axes 1, 0, 0, 0, 1, 0, and 0, 0, 1 are what we call basis vectors. It's pretty obvious how we knew that the length of the 2, 0, 0 vector is 2. Any vector that is just a scaled version of a basis vector like this is going to have a really obvious length. But what about vectors like this, like 1, 2, 0? Well, we can just use Pythagorean's theorem to figure this out really easily. A squared plus b squared equals c squared, so 1 squared plus 2 squared equals c squared. So the length is the square root of 5 here. When we talk about a vector's direction and magnitude, the direction is almost always a unit vector. That way, the length is always 1, and we don't accidentally scale our objects when we multiply things later. For example, sticking with the vector 1, 2, 0, if we were to make this vector a unit vector, we'd end up with 1 divided by the square root of 5, 2 divided by the square root of 5, 0. This is because, as we discussed, the length of this vector is the square root of 5. So to make it have a length of 1, we just divide the whole thing by the square root of 5, which means that we divide each component of the vector by the square root of 5. To get the original vector back, we just multiply this unit vector by the square root of 5. Now, I want to go back to basis vectors for a second. 1, 0, 0 is the basis vector corresponding to the x direction. 0, 1, 0 is the basis vector corresponding to the y direction. And 0, 0, 1 is the basis vector for the z direction. Real quick, you might want to pause this video and see if you can get these basis vectors to line up with your thumb, index, and middle finger on your right hand to test out the right hand rule that I talked about earlier. One weird quirk is that these basis vectors are somewhat arbitrary, and usually defined in terms of other basis vectors in a different coordinate space. That probably sounds very odd, so let me try to explain. Let's say that our lives took a really bad turn, and we found ourselves working for Microsoft and using DirectX. We'd be using the left-hand rule instead of the right-hand rule. That means our z-axis will be inverted, or effectively multiplied by -1. But the way we're thinking about it, that dumb Microsoft z-axis is only defined in terms of the right-handed z-axis, just multiplied by -1. But if you're used to using the left-hand rule like this, you wouldn't think of the z basis axis as being 0, 0, -1 compared to the right-handed rule. You just think of this as 0, 0, 1. This is the z-axis according to you. And the right-hand rule, z-axis, would seem to be 0, 0, -1 from your perspective. We could even use really bizarre basis vectors like this, where this really long guy would be our x basis vector, and this guy going out here would be the y-axis. Then, if we had a vector like this, 2, 0, 0, in this coordinate frame, it would result in this larger version of this weird vector, since it's just a version of it that's scaled by 2. If we had a vector like this instead, 2, 1, 0, where the only difference is that 1 in the y coordinate, then we're essentially shifting this vector by our weird y vector. We are adding the y vector to our previous 2, 0, 0 result. If we just look at the numbers, this is very easy to understand. And if we go back to the visual interpretation, which of course we should be interested in since we're all talking about computer graphics, then we're essentially taking the tail of this y vector, placing it at the tip of the x vector, and tracing a new vector from the origin to where the tip of this y vector lands. What's nice is that we could instead start with the weird y vector and add the weird scaled x vector to that, and the tip would end up at the same place. We'd end up with the same final resulting vector. This is called the commutative property of vectors, in case you care. I had to Google this just now. Sticking to this same weird coordinate frame, 2, 2, 0 would be adding a version of our y basis vector that's scaled by 2 to the scaled version of our weird x basis vector, resulting in this vector. Now, I know that this is maybe a little mentally exhausting if you're thinking about basis vectors this way for the first time. We could use these basis vectors to figure out how to represent our vectors and points like we just did, but would you really want to? Part of why this is so difficult is because we're defining these basis vectors, or in other words, this coordinate frame, in terms of our nice basis vectors that we're used to using. Of course, we'd prefer to just stick with our simple grid-based system that these basis vectors give us. In this coordinate frame, without me needing to give much of an explanation, you probably know what 2, 2, 0 looks like as both a vector and a point. If you need to rewind this several times for this to make sense, that's completely okay. This took me a while to grasp the first time as well. One key concept here is that regardless of which coordinate frame we're using, any vector in that coordinate frame is the result of adding scaled versions of these basis vectors to one another. For example, 1, 0, 0 in this coordinate frame is just 1 times this basis vector plus 0 times the other two basis vectors. 2, 0, 0 effectively scales that x basis vector by 2, leaving us with this. Let's go back to the 2, 1, 0 vector. We've just added the y basis vector to the previous result, leaving us here with this vector. I know we've been talking about vectors and points for a while now, but remember when I said that I think of points as being sort of moved away from the origin? Well, it can be very helpful to think of points as starting at the origin and being shifted around by the scaled versions of these basis vectors. Looking at this animation, you can see the point going along the x-axis until it hits the 2 marker, then going up 1 unit. But you can also think of this as moving along the actual vector 2, 1, 0. Now, frankly, the whole explanation in this video is extremely overkill for this triangle rendering project, but it's very important that you have that intuition for vectors. I'd argue that the most important thing to have for computer graphics is this intuition of vectors. Of course, we'll dive into this a lot in the upcoming projects, so this will be second nature in no time, even if it seems overwhelming right now. You do not have to have understood everything I just said, but it would be helpful to try to understand as much of it as you can right now, but you can always come back later. For this project, you're just sending 3 vertices up to the GPU to represent the points of the triangle. And you'll run a couple small sub-programs called shaders to color that triangle, which we'll get into in the next video.